of pKa. pKa is a measure of acid strength. It's related to KEQ, the equilibrium constant. When it transforms into acids, we're talking about the Ka, or acidity constant. But for us, pKa is simply going to be a measure of acid strength. It's related directly to the Bronsted-Lowry definition. And best way to think about pKa is the ability to give up a proton. So pKa is the ability to give up a proton. That's the main thing that we should be thinking about for its context. We're going to have a series of compounds that I want you to memorize. First and foremost, there's a small periodic table trend that you should memorize, and it's electronegativity. In the periodic table, we have carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, phosphorus, silicon, a few other atoms. The periodic table trend for electronegativity goes this way. If we're comparing electronegativity of atoms, it increases going from left to right across the row, and it increases going from bottom to top in a column. Okay? This is a very important trend to recognize. For simple acids, where we're comparing carbon, nitrogen, oxygen, and fluorine, where they're attached to hydrogen, where we're actually comparing the strength of this carbon, nitrogen, oxygen, hydrogen, fluorine, hydrogen, chlorine, hydrogen bond, bromine, hydrogen bond, iodine. Well, I had a better first start this morning. I'll need to find some whiteout for this. But iodine hydrogen bond, and there's other things, we have sulfur hydrogen below here, phosphorus hydrogen, silicon hydrogen. There's a periodic trend which describes the ability of these types of substances to donate a proton or be more acidic. The acidity trend in the periodic table increases again from left to right, and instead, this time from top to bottom. The reason was in the pre-lecture video. It's not important that you actually know the reasons for this, but this particular periodic trend you have to put to memory. If we were comparing carbon, hydrogen, nitrogen, hydrogen, oxygen, hydrogen, fluorine, hydrogen bonds, you'd have to be able to rank that this is most acidic, second most, third most, fourth most. If you were ever asked to compare these four acids, hydroiodic acid is stronger than HBr, HCl, or HF. Okay? So you need to put this particular trend to memory. We're going to talk about this particular series right now in terms of its exact specific pKa, and these are numbers that you are going to have to memorize or put to memory. Flashcards are probably the best thing for this particular thing, but first we know the general trend. We're going to look at four species we're comparing here and their strengths of their respective heavy atom hydrogen bonds. This is a measure of their acid strength. We have these four compounds going across the periodic table. We already know that HF is stronger than water, is stronger than ammonia, is stronger than CH, because on the last slide that I had drawn out here for us, that's exactly what we drew. But what I want us to know is that the pKa for a carbon-hydrogen bond in methane, the pKa, is equal to 48. This number you should memorize. The strength of this particular bond in ammonia, the pKa we're going to use in this class is 38. For water, 15.7. For HF, 3.3. These particular numbers I want you to put to memory. Okay? It's important that you memorize them because I'm going to ask you to use them on the second exam that we have together. There'll be a total of about 12 numbers that I'm going to have you put to memory. First thing we can note, though, is that acidity increases going across the row in the periodic table that follows the trend, and these specific numbers are important. This tells us that this compound is definitely acidic. So 3, that's a acid for sure, what pK means just from a practical point of view. Water, we drink it, right? This is not very acidic. Last time I tasted water, my throat felt just fine and refreshed. I did it about 10 minutes ago. This is not very acidic. What does 48 mean? It means like the weakest possible acid in the universe. pKa of 48, compound is not acidic whatsoever. Okay? pKa is related to the strength of these particular bonds. HF bond breaks easily. It's highly polarized, donates a proton easily. OH, what we saw earlier today, it can donate a hydrogen in the form of a proton to a base if it's strong enough. Ammonia is not very acidic, and methane, definitely not acidic at all. Okay? You'll notice that these also increase in polarity. So we have increasing acidity. This is a strong acid, weakest possible acid maybe in the universe, or one of the weakest possible acids. We're going to draw their conjugate bases right away. So if you were feeling a little shaky about conjugate acid-base theory, we're going to draw the conjugate bases of these species right below them. If methane actually gives up a proton, just we remove a proton and leave behind the electrons, we are left with this species. If it's a little unclear what I've drawn here, it means the same thing as this Lewis structure with two dots here, but I'm going to be using this single line here frequently to represent a pair of electrons. Okay, let's do the same thing with nitrogen here. We'll make its conjugate base. We saw it once today. It's called amide. Water would be hydroxide. Again, I'm just drawing conjugate bases. If these species gave up a proton in an acid-base reaction, these would be the resulting conjugate bases. From your pre-lecture video, you should know that this was increasing acidity. And we talked about in the pre-lecture video what the basicity trend should be for these conjugate bases. We also mentioned it in the first few minutes of lecture today, is that a strong acid has a what type of conjugate base? Strong acid, does it have a strong conjugate base or weak conjugate base? Strong acids have very weak conjugate bases. A weak acid, and this is the weakest possible acid we can imagine, or one of the weakest that can be even measured, does never give up a proton in an acid-base reaction, very rarely. If this is the weakest possible acid we can imagine, then its conjugate base is the strongest. Or we could just say strong conjugate base. So notice that the acidity trend in a row of the periodic table, carbon, hydrogen, nitrogen, hydrogen, oxygen, hydrogen, F, hydrogen, increases. The conjugate bases are opposite. This is a very, very important thing for you to recognize. We'll look at the other trend that we saw in the periodic table going down a particular column. We'll just review this particular trend here. We did this one right now. We're going to look at this one. Okay. So if we're comparing going down a column in the periodic table, HF, HCl, HBr, HI, if we want, we can fill in the correct octet of electrons for these particular compounds. Acidity increases going down. This is the strongest acid. We're not going to put the pKs for these ones, not important for us to know. But if we draw the conjugate bases of these four species, you should be able to do it right away. We just did the conjugate base of HF, it was F minus. Chloride is the conjugate base of HCl, bromide, and iodide. If HI is the strongest acid, then I minus will be the weakest base in this series. And so, this is increasing basicity from weak to strong, going converse related to acid strength. So this general idea of strong acids giving weak bases or weak acids giving strong bases holds true. So I want you to know these trends that I'm drawing here in arrows, be able to use them. If I put these four species in a random order, I'd like you to rank them. If I ask you what their relative basicities are, it would be I minus, Br minus, Cl minus, F minus. If these four acids were presented to you, in some random order, you should be able to very quickly look at a periodic table, identify that HI is the strongest, HBr, HCl, and HF, and rank them in that particular order. That's the purpose of me putting this particular trend here. Here's going to be 4 more species that will actually put to memory what their pKa values are. The last 4 were a periodic 4. These 4 that were in our notes right here. Those 4 pKa values you need to know. And these 4 compounds are not in a periodic trend per se, but these are very, very common organic functional groups that participate in acid-base reactions. And so it's important that we have a general idea what their pKa's are. Let's start with methanol.